Well, thank you very much for that introduction. It's really an honor and a privilege to be here, and I thank the section for this honor. I'd like to think that over the course of my career, I have somewhat successfully emulated Reginald Daly's record of carrying out petrologic and chemical studies that have all been motivated by field observations. So it's very nice to be giving a lecture in his name. I also have a bit of a personal connection, which is that it turns out my father was Reginald Daly's doctor in the last years of Daly's life. So what goes around comes around, and I'm very pleased to be here. So I will be talking about chlorine-stable isotopes at convergent plate boundaries, both in subduction systems and during convergent metamorphism in general. And to get started, before I get into the details, I want to acknowledge that I am talking about results, data that have been collected collaboratively with Zach Sharp and building extensively on the work of our former student, Jamie Barnes, and also building on a lot of data and ideas from many, many other people. Although for the rest of this talk, I'm mostly going to subject you to my own data and ideas. So here we go. All right, a little bit about the motivation. I think there's quite a number of people in this room who have spent a lot of time thinking about recycling processes at convergent plate boundaries. So we know that we have variably hydrated and carbonated materials that enter subduction zones, go down to depth, devolatilize. Volatiles play a key role in triggering melting of the mantle wedge, erupt as arc volcanoes. Material gets eroded and transported back into the system again. And it's clear that fluid does a lot of the work associated with mass transfer in subduction systems, but we don't necessarily know that much about all the details of how this happens. So as you can see, we have many different kinds of rocks that have different volatile contents at different positions in the subduction system. But if we're interested in studying specifically what fluid does, we have a little bit of a problem. We can study fluids in the laboratory and do experiments and so on to study dissolution of different minerals, solute transport, and so on. But when we're dealing with rocks from exhumed subduction complexes, the fluid is long gone from those rocks. So it can be a little bit of a challenge to try and understand exactly what fluids we're doing at different points in the subduction system. And I would argue that at this point we have sort of first-order knowledge of quite a number of the important volumes and fluxes of mass in subduction systems, but that when it gets down to the details about exactly how fluid moves around in the subducting slab and into the overlying mantle wedge, I think we know a lot less about this. And this is mostly what I'm going to focus on in this talk. It's going to take a little while to get to this point, however, so bear with me. Okay, so the big question here is if we have all these stacked up rocks, serpentinites, blue schists and eclogites, sedimentary rocks all going down the subduction zone, how do fluids get out of these rocks? We think serpentinites are the major source of aqueous fluids that get liberated at convergent boundaries. How do those fluids pass through the overriding material? How do they move around once they get into the mantle wedge? Are they channelized, percolative? Do we have a lot of mixing? And I think the answer to all these questions is yes, but we don't really know that much about all of the details. So what I'm going to do in this talk is try and convince you that chlorine-stable isotopes can help us to get at some aspects of how fluids move around in subduction systems. And for those who aren't familiar with chlorine, we have two stable isotopes, chlorine-35 and 37. And I'm going to talk about all the data using standard delta notation, where the standard that we reference all of our data to is standard mean ocean chloride. The delta 37 Cl value of that has a defined value of 0 per mil. So we're going to be looking at differences relative to seawater. And if you look at a compilation of all the published data, almost all the published data of subduction inputs and mantle rocks it looks like this, and I managed to leave off, unfortunately, all the authors whose work this comes from. But you can see here's sedimentary and basement pore fluids in oceanic crust. Here we have sediments, oceanic sediments, and high and ultra-high pressure metasedimentary rocks, altered oceanic crust from modern crust, and a few high-pressure metamorphic equivalents, ocean serpentinites, seafloor serpentinites, high-pressure metamorphic equivalents, mid-ocean ridge basalts, and some data from ocean island basalts. And when you just look at this plot, here's seawater, and most of what we think is the mantle is in this gray band right here. It's a little bit discouraging for using chlorine isotopes to tell us anything about sources and sinks and migration paths and subduction zones, because in most cases, the total variability is very small. It really goes from about +2 to -2 per mil. So it's not obvious when you just look at a compilation like this that chlorine-stable isotopes are going to help us to learn anything that we don't already know about subduction systems. But I'm going to try and change your minds about that. So we'll see how well I succeed. All right, so we're going to start from two assumptions. One is not really an assumption. I think we would probably all agree that chlorine really likes to go into hydrous fluids. Lots of the fluids in crustal rocks in particular are saline brines. And from theoretical work, it looks as though chlorine isotopes, so 35 and 37 Cl, shouldn't undergo any significant fractionation during devolatilization once rocks are in the metamorphic realm. So in other words, at elevated temperatures, it's expected that there will be no isotopic fractionation associated with devolatilization. We're going to test this assumption as we go along. But if it's true, then what it says is as a downgoing slab undergoes devolatilization, fluids that get released in those reactions will carry the isotopic signature of the source rocks with no correction needed. It will be exactly the same as that of the dehydrating rock. And if this is true, then we should be able to use chlorine-stable isotopic compositions of rocks in different structural positions or whatever to actually trace out fluid pathways. So, as I say, we're going to test some of this as we go along, but that's sort of the starting premise of this talk. All right. So, before I get into the details of some case studies, just a little bit about where chlorine is housed in rocks. Some of it substitutes directly for OH groups in minerals, for example, clays and micas, apatite, and so on. This is a biotite right here. Some of it appears to be adsorbed along grain boundaries. This is a chlorine X-ray map. You can see the chlorine around. This is a quartz grain right here. This is clay over in here. And some of it is in saline fluid inclusions. And for the purposes of this talk, I'm going to divide up these different types of chlorine. We're going to talk about structurally bound chlorine, where it's bound up in minerals. And there's a little asterisk here that I'll come back to later on. And the chlorine that's adsorbed on the grain boundaries or is in fluid inclusions, this is water-soluble chloride. And for many of the samples I'm going to talk about, I've analyzed structurally bound and water-soluble chloride separately, but I'm also mostly going to be talking about bulk delta 37 Cl data from including both of these components of the chlorine. Okay, so I'm going to walk you through three stories. And the first one that I'm going to spend the most time on actually doesn't have anything to do with subduction, but it is a chance for us to ground truth our assumptions and the theoretical predictions about the behavior of chlorine-stable isotopes during prograde metamorphism. So we're going to start out looking at two sequences of rocks, Triassic continental sedimentary rocks and Jurassic marine rocks. And we're going to trace them from a locality here in the Jura Mountains where they're unmetamorphosed. And we're going to follow them up metamorphic grade, starting at very low metamorphic grades and ending up at about 575 degrees in the amphibolite facies. So we're going to track prograde devolatilization of these rocks and look directly at the effect that has on chlorine-stable isotope behavior and what we can and can't say. All right, the second example is going to come from these blue units over here. All of these examples are going to be in the Alps. The second one comes from the Zermatt-Sass ophiolite, which is a sequence of high and locally ultra-high pressure metamorphosed oceanic rocks. So serpentinites, altered oceanic crust, and metasedimentary rocks, all part of that ophiolitic package. So in this case, we're really going to be looking at some of the fluid rock interactions that happened while the rocks were in the subduction system. And then lastly, I'm going to talk about an example from here in the Ivrea zone, where we're going to look at some mantle wedge rocks that are exposed at the Earth's surface and look at how fluids interacted with those mantle peridotites. And I just want to stress that these rocks are pre-alpine, so I'm not talking about a single subduction system here with things happening in different places all at the same time, but I'm using them simply as 3 different case studies of how fluid rock interaction leaves a record in the chlorine isotope system. All right, so we're going to start out, we're going to look at samples we collected here from a quarry in the Jura Mountains, and then we'll look at the data from the metamorphic equivalents. All right, so here's this quarry, and in the lower part here, these units that are labeled Kuiper, these are all uppermost Triassic rocks of continental origin. So at the bottom here, we have a sequence of fluvial and deltaic sediments, overlain by a sequence that is dominated by playa lake sediments. And then we go up from those directly into this black shale sequence, and these are all of marine origin, and they include black shales and organic rich limestones. All right, and what I've shown here is the stratigraphic column, and then the chlorine isotope composition of rocks from different positions in these 2 sequences of rocks, the Liassic and the Kuiper. And over on the right here is just the chlorine concentration in the different rocks. There's a lot of different symbols on here. Mostly I want you just to look at the stars. These are the bulk chlorine data for the samples. So here are the isotopic compositions. And what you can see right away is that there is huge variability in this single quarry. Total of 5 per mil range in chlorine isotope composition. When I said that most of what we see in the subduction system in the rocks is only 4 per mil total variation. So, and what you can see here, where there are multiple stars all for the same horizon, those are samples collected along strike from each other within a single sedimentary layer. And you can see then that there are that single layers are isotopically homogeneous, but there are large differences that exist between different layers. So the samples are isotopically extremely heterogeneous to what we've seen thus far in the subduction record, and within each layer they seem to be isotopically homogeneous. Very briefly, the blue triangles are water-soluble chloride data, and the red diamonds are the structurally bound data for the same samples. And I'll come back to those data later on. But what I want to do now is go from this baseline in this sedimentary sequence, and based on the many, many years of work by Martin Fry, we can trace these same 2 sequences, the Kuiper rocks and the Liassic black shales, we can trace them progressively up metamorphic grade in a transect leading to the Lukmanir Pass in northernmost Italy. So we go from that same rocks that we saw in the quarry. Here are now their amphibolite facies equivalents. These are the Triassic rocks right here, and in the foreground are the equivalents of those Liassic black shales. These are blocks that have come from these exposures up here at the top of the photograph. And what we find, to make a long story short, is that if we look at all of the data from all the different sample profiles that we collected through these 2 sequences, we find for low metamorphic grade, green schist grade, amphibolite grade, and a lot more profiles that I'm not showing, they all show the same thing, which is that we see large heterogeneity still present even up to high metamorphic grade. So in other words, we're not seeing a general smoothing of the chlorine isotope compositions with increasing temperature. All right? And again, we find that single layers tend to be reproducible, homogeneous. here again. But as we go between layers, we see changes in the isotopic composition. And this persists all the way up to high metamorphic grade. Again, this is not a subduction complex, but it does let us see what's happening as we increase temperature and the rocks undergo prograde devolatilization reactions. Just very quickly, a look at what's happening with chlorine concentrations during metamorphism. This is now log scale. In this and subsequent diagrams, the blue is always the Liassic, and in red, these are the Kuiper rocks, the Triassic continental rocks. And what you can see for both sequences of rocks is that there's almost immediate loss of chlorine going from our sedimentary rocks in the quarry to the lowest metamorphic grade. And these are rocks now that are in the 200 to 300 degree range for maximum temperature. But then from there on up to high grade, there's really not that much change. There's certainly no systematic change in chlorine concentrations. So we're seeing chlorine loss at the beginning of metamorphism and then not much change after that. And I simply want to point out these blue samples here from the Lias, they all come from a major shear zone, and they've clearly been isotopically reset, and you see that in other isotopic systems as well. But if you look at the other localities and these data here, you see that roughly there's no change in concentration. And if we look at all the data in terms of chlorine isotopic composition, we see more or less the same thing. There's a lot of scatter at different localities, but if you look at the median for each population, which is the horizontal line in each of these boxes, they're broadly constant except within this shear zone from sedimentary conditions to middle amphibolite facies conditions. I meant to point this out right here, that you can't correlate all of the different sedimentary layers from sedimentary conditions to the metamorphic equivalents because the playa lake facies actually pinches out to the south. So here at the locations in the Glarus Alps, some of the playa facies rocks are still present, but as we go further to the south and up metamorphic grade, we lose those rocks and the section becomes dominated by the equivalents of these fluvial rocks right here. Okay, so it's a little bit hard to see exactly how these relate to these unless we parse that a little bit more. Now, these are the full cohort data. What I really want to do now is take a look at single bulk compositions and what happens to their chlorine isotope composition as we go from sedimentary protolith up through the different metamorphic facies. So now what I've plotted on here, I've taken bulk compositional data, so major and trace element data, for a large suite of samples from each of the different localities. And I've correlated their bulk compositions. So I compare one rock with another one. And if the bulk compositions are correlated with R-squared values greater than 0.95, they're included on this plot right here. And most of them have very low R-squared values, and you can't correlate from place to place exactly. But these samples show very nice correlations. So what we have here are two samples from the same green shale horizon in the quarry in the Jura Mountains. And all of these other green dots are rocks that are compositionally identical to those green shales. And here are showing the chlorine isotopic composition. The error bars here are plus or minus 1 sigma. And you can see that I can fit a horizontal line through all of those data points, saying that statistically there is no change in chlorine isotope composition going from sedimentary protoliths all the way up to temperatures on the order of about 550 degrees. Now, for some of the other rock types, there just aren't that many that correlate really nicely. But for all of those that do, almost all of them, again, I can fit a horizontal line, and within the 1 sigma uncertainties, rocks have identical isotopic composition. Different bulk compositions have different isotopic composition, but any single bulk composition stays constant. The one exception is this red shale here and its correlatives. The dashed line is a best fit line, but now with 2 sigma uncertainties shown instead of the 1 sigma, again, all of the data are statistically identical. So I think this goes a long way towards confirming some of the theoretical predictions that there is no chlorine isotope fractionation during prograde devolatilization of the rocks. So in other words, when I see a metamorphic rock that has the same composition as this rock here from this same setting or series of rocks, it will not have changed its composition during 500 degrees of metamorphic devolatilization reactions. All right. Now I just want to briefly talk about some differences between the structurally bound chlorine data and the water-soluble data. So this plot takes a little explaining. Over on the left now, instead of little delta 37Cl, this is big delta. So this is now the delta 37Cl value for the structurally bound chloride in a given sample minus that for the water-soluble chloride in the same sample. All right, positive values here mean that the isotopic composition of the structurally bound component is higher than that of the water-soluble component. And you can see for the Kuiper samples, the red dots, they essentially all, except this one right here, show that relationship. And this dashed line here is the equilibrium fractionation curve. And to first order, these samples fit quite nicely with that equilibrium relationship, suggesting that the structurally bound chloride and the water-soluble chloride fraction actually equilibrated with one another and have maintained that equilibrium relationship such that samples that equilibrated at over 500 degrees centigrade haven't been reset during any subsequent infiltration of groundwater or whatever on their way back to the Earth's surface. But if we look at all the blue symbols here, the Liassic black shales and their equivalents, they show opposite fractionation. So for all of them, the structurally bound chloride is lower than that of the water-soluble chloride. In other words, the water-soluble is enriched in the heavier isotope. This is backwards from all of the theoretical predictions for equilibrium fractionation between a silicate and a coexisting briny fluid. So how are we going to explain this? And I think to explain this, this is going to become important for the other case studies I'm going to talk about, we have to know something about where the chlorine is housed in these rocks. And if we look at the Kuiper, those continental Triassic rocks, we find that the chlorine is always concentrated in clays and micas. And here are just two different samples, backscatter electron image and a chlorine X-ray map. These are both amphibolite facies samples. But you can see there's several hydrous minerals here, chloritoid, chlorite, biotite, muscovite. But the chlorine is preferentially incorporated in the biotite. All right, in the lowest grade rocks, it's in the clays. As we go upgrade, it goes preferentially into biotite. And you can see here's a staurolite and a biotite, and again, the chlorine is in the biotite. In general, the concentrations are less than 0.1% chlorine, and fluorine concentrations are always higher than chlorine in these micas. Now let's take a look at those black shales that show the weird fractionation behavior. And what's really intriguing about these rocks is that even up at 550, 575 degrees centigrade, there are microfossils that are recognizable in the black shale equivalents and in the organic limestone equivalents. And all of these little microfossils have a lot of organic carbon surrounding them and within them and so on. And it turns out that if we do X-ray maps on the microprobe, this is for carbon and this is for chlorine, it turns out the chlorine is all housed in that organic matter. It's not in the micas, it's not in the other hydrous silicates, it's not in apatite. It's all associated with the organic matter. And here's just a couple of other examples. Here's a thin section view. You can see a very organic rich band in here. And again, there's the carbon map. Here's the chlorine. It's all with the carbon. Another example here is a little microfossil, carbon, chlorine, and in this case, there's actually iron associated with them as well. And these organic rich patches, in some cases, have up to 2 weight % chlorine in them. So this was a real surprise. So the chlorine in all of the Liassic rocks seems to preferentially be housed in organic matter, which means we're dealing with various organohalogen compounds, not chloride replacing OH in silicates or apatites. All right, so let's go back now. Oh, actually, before that, so organochlorine compounds. This is something I knew nothing about. Lot in the environmental literature about man-made organochlorine compounds, but it turns out there are about 5,000 different naturally occurring organochlorine compounds, mostly in marine environments, but not totally. And just as an example, marine red algae of this particular family, 480 different chlorinated organochlorine compounds have been found in this single type of red algae. And chlorinated compounds are also produced by all kinds of other marine organisms. So maybe it shouldn't be a surprise to find chlorine associated with carbon in marine sediments. So now let's go back to what these big delta values are trying to tell us. So again, we had the Kuiper rocks that seem to show an equilibrium fractionation between structurally bound and water-soluble components. And I've added on here some data from Jamie Barnes. These are seafloor serpentinites from the Isobonon Marianas setting, and they seem to fit quite nicely with that equilibrium relationship. I've added some of her sedimentary data too, and what you can see is that most of the sediments that she looked at, seafloor sediments, actually have the same backwards relationship as the black shales that I've been looking at. There's a few that show the normal relationship, but most of them have the backwards fractionation. Okay, well, are we looking at some kind of equilibrium fractionation between organochlorine compounds and brine? Well, here's the equilibrium prediction, the theory, about what that fractionation should look like. And pretty clearly these blue boxes don't meet don't fall along that equilibrium curve. So what's going on? Well, here, if we turn to some of the biochemistry literature and some of the environmental literature, it turns out that there are a number of biosynthetic pathways for making organochlorine compounds that result in very large kinetic fractionation effects. So here's just one example. This is chloroperoxidase mediated chlorination. So here we have an organic compound that's got hydrogen bounded to it, and the reaction goes here and puts chlorine into the organic matter and releases water. For every one of these systems that has been studied experimentally, it turns out there is this large kinetic fractionation, well, not always large, but there is kinetic fractionation in which the 35 chlorine, the light isotope, preferentially goes into the organic matter and leaves the aqueous fluid around it enriched in the heavy isotope. And that's exactly the effect that we're seeing in all of these marine sedimentary rocks and their metamorphic equivalents. So for the CPO-mediated reaction here, several different studies have been done, and they show that there's a kinetic effect of up to 12 per mil, where this is isotopically light compared to the starting chloride. There are several other pathways, enzymatically mediated pathways that have been studied, and they have fractionations ranging from 0 to about 3 per mil. But in every case, they would drive the rocks down to this field that we see the blue in. So I think we're looking at a signature of low temperature chlorination of organic matter that is preserved from the sedimentary realm all the way up to amphibolite facies metamorphic conditions. All right, so let's sum up this prograde sequence and what we've learned, and then we can go on and look at different parts of the subduction setting. So first of all, the sediments show a surprisingly large degree of isotopic heterogeneity, and that heterogeneity is preserved during prograde metamorphism. There is indeed no chlorine isotopic fractionation that occurs during devolatilization, even at the lowest metamorphic grades. Surprisingly, in the marine rocks, chlorine turns out to be stored in organic matter, and it's stable there to over 500 degrees centigrade. And some of these organochlorine compounds might give an isotopically light signature to the rocks that contain them. It's been a puzzle for a while how we make isotopically light compositions, and this may be part of the answer right here. And I'm going to come back to this at the very end. I think organic carbon may turn out to be an important chlorine reservoir in subduction zones. so that chlorine might be tied to the carbon cycle as well as to the water cycle at convergent plate boundaries. All right, that was a lot. Let's more quickly go through 2 other case studies. All right, first of all, the Zermatt-Sauce ophiolite. This is on the south side of the Matterhorn, a very large intact package of ophiolitic material. And I'm going to focus specifically on serpentinites that have followed the PT path broadly described by the green arrow here based on data from all of these people. And what I'm going to do is for all the samples that we collected from this ophiolite, we correlated the serpentine compositions and the textural features with a huge previous study that had been done by Lee et al. In these same rocks in 2004. So his work, he identified about 6 different stages of serpentinization and deserpentinization, recrystallization, and we found evidence for 4 of those in our samples. So type A starts with seafloor pseudomorphic replacement of olivine and pyroxenes. We go through a subduction phase here with myelinization and recrystallization. Recrystallization that occurs during exhumation, and then a green schist overprint down here. And again, we've correlated all of the compositions and the textures for each sample with Lee et al.'s very large database. All right, so now if we take a look at the chlorine isotopic composition of each of these different stages of serpentine, what we find is the earliest stage, type A here, has an isotopic composition. There's only 3 samples, unfortunately. It's rare to preserve the early serpentinite fabrics, but they are in the exact same range as data from Jamie Barnes from serpentinites that were serpentinized directly by seawater. All right, we go further down the subduction zone and we get data that plot here. Statistically, they're identical to the earlier ones. But now we're going to turn the corner and start the exhumation process. And these texturally younger serpentinites have isotopic compositions that are considerably lighter and statistically significant. And lastly, the green schist overprint down here, we still have light compositions, and there are a number of veins associated with these. Fluid inclusions and the compositions of the veins are essentially identical. So what we see is that during the prograde subduction, the composition of the seafloor serpentinites is retained. It's only during exhumation that we get different isotopic compositions of the serpentinites. And now if we look at all of those data together, I've added on here compositions of oceanic sediments from the Zermatt-Sauce ophiolite and from the diamondiferous rocks at Lago di Chignana, which is part of the same system. And what you can see is that the vast majority of them have very low isotopic values. And I think what we're looking here is a very simple 2-component mixing story, that during prograde subduction of the serpentinites, there's no change in isotopic composition. But as the rocks turn the corner and start their path back towards the surface in the subduction channel, fluids seem to have been released by metasediments in the same sequence, and those fluids have interacted with the earlier serpentinites and caused and have lowered the isotopic composition. So these data are now telling us that serpentinites preserve their seafloor values during subduction to at least 80 kilometers depth, maybe greater. But during unroofing, we get localized reactions that cause mixing with fluids derived from the sediments that have also gone down the same subduction zone. And so that mixing is only happening during the exhumation phase. So this modification, if we just looked at all of the data together without the textural correlations, we'd say, wow, there's this huge range compared to seafloor serpentinites, and that's not the case. It's only during exhumation, devolatilization reactions are driven in the metasediments. Those fluids then react with the serpentinites in melanges, in veins, and so on, and impart a different isotopic composition. Okay, last example. Now we're going to turn to this chunk of metasomatized mantle that's exposed in the Ivrea zone. And we're going to look at 2 peridotite bodies. The Balmucha peridotite is dominated by spinel larzolite that's seen only a little bit of partial melt removal. and shows very little evidence for metasomatism based on lots of other people's work. In contrast, the phaneroperidotite body is Spinel-Harzburgite. It's had a large amount of mid-ocean ridge basalt type melt extracted from it, and then it subsequently underwent extensive metasomatism. And the metasomatism appears to have occurred at about 900 degrees and 1.2, 1.6 GPa. So fairly shallow levels, but in a super subduction zone mantle wedge setting. All right, and at Phenero, we see 4 different types of rocks that I'm going to focus on. One I'll call type 1. These are peridotites that have very minor bits of amphibole and phlogopite that are distributed evenly throughout the rocks. Type 2 are phlogopite rich, where you can see concentrations of phlogopite. Type 3 are large amphibole rich segregations. They also have phlogopite in them, but they're dominated by calcic amphiboles. And then type 4 are segregations that are made up almost entirely of phlogopite. So we're again going to take a look at the chlorine isotope compositions of these rocks. Here is our reference data set for mantle compositions. Balmucha peridotite sits nicely in that same field. And now we have the 4 different types of samples from Phenero. And you can see there's much more scatter in each population. But there's no way we're going to be able to explain these data as any kind of simple 2-component mixing. So we have mantle-like values, but we have things that are pulled to higher chlorine isotope compositions and to lower values as well. So we have to be looking at least a 3-component mixing system here. So just for reference, here's now altered oceanic crust data, modern seafloor plus my high pressure data. Same for serpentinites and rhodongites. And then here are my data from high and ultra high pressure metasedimentary rocks from the Zermatt-Sauce sequence, just for reference. And you can see that some of the high values at Phenero look a lot like AOC and high pressure serpentinites. And the low ones start trending towards the sediments here. We can add another isotope here and look at hydrogen isotope systematics as well. And if we just looked at the hydrogen data, we'd be looking at 2-component mixing between a mantle end member here and some higher delta D value. But when we add in the chlorine data as well, we're clearly looking at some kind of at least 3-component mixing. And now I'm going to add in data where we have both hydrogen and chlorine data from high and ultra high pressure metasedimentary rocks. These are the Zermatt-Sauce data, and they plot in this field here. These are now Jamie Barnes data from a paper that's in press on high pressure serpentinites and altered oceanic crust. And if we think about these rocks going down a subducting slab and undergoing devolatilization, the fluids that get released are going to have higher delta D values than the minerals with which they're in equilibrium, but there'll be no change in delta 37Cl based on all the data I've already shown you. And you can see that these data fit very nicely with this 3-component mixing model. So that we start out with pristine mantle and we have at least 2 different fluids derived from different subduction components that are percolating through these rocks. And they're doing so both pervasively, causing grain scale alteration and growth of micas and amphibole. And we also see evidence for channelized flow. So this tiny little phlogopite seam right here has higher delta 37Cl and delta D values than things on either side of it. And the same in this horizon right here. But this shear zone right here actually shows no change in delta 37Cl. So we're seeing both pervasive grain scale flow and channelized flow. So if we sum up these data, we find that the chlorine isotopes very nicely fingerprint discrete mixing components coming from different parts of the subducting slab. So one component that appears to be altered oceanic crust plus or minus serpentinites, and one that is coming from subducted sedimentary material. And we find evidence for both channelized and percolative fluid migration. And we can start to really map out the spatial scales of fluid rock interaction. Very briefly, I would just like to try to put some of these results in the context of some recent physical models for fluid migration in subduction systems. There have been a large number of papers in the last few years modeling what or how fluids can actually migrate during devolatilization in a subduction system, summarizing several papers by Facenda and others. In this case, we're looking at the effect of slab bending as rocks enter the subduction zone, followed by unbending down at depth. And bending is going to cause infiltration of fluids, both seawater and accretionary pore fluids from sediments, down into the oceanic crust and mantle, causing serpentinization. And then unbending stresses down at greater depths are going to drive fluids in patterns that may not be intuitively obvious. So there is both cross-slab fluid flow, both outwards and inwards. There is flow up dip here within the mantle part of the slab, and then there's a zone of focused cross-slab migration right here. So you can see both up dip flow, which would tend to preserve isotopic compositions. There'd be no mixing, you're in single horizons. But then everywhere there's cross-slab flow, you have the potential for getting isotopic mixing and communication between different lithologies. Another recent study by Wilson et al. This is now looking at the effect of compaction and also devolatilization of many different rock types, not just the serpentinites. And basically, if there's no compaction involved, so the solid rheology isn't coupled with the fluid flow, you just get buoyant rise of the fluids. But when the solid rheology is incorporated into the model, again you see a zone of strongly concentrated fluid flow that's up dip within the slab. This is going to tend to preserve isotopic compositions on a large scale. But then there are areas of very focused cross-slab fluid migration, and these are the places where we might expect to see that the chlorine isotopes are going to be reset by mixing. All right, that was a lot. Let's see if I can sum all of this up. All right, so what are some of the things that we learned from looking at chlorine? First of all, when we look at sedimentary rocks, or I would extend this to any types of rocks, protolith heterogeneities are present, generated at low temperature in the case of the sediments, things happening in the sedimentary depositional environment. And those heterogeneities are preserved throughout metamorphism. There's no fractionation when fluids are released from those rocks. And overall, all of these studies are showing us very limited communication between different lithologies in all of the different packages of rocks. And in the case of the Zermatt-Sauce rocks, that's true throughout the prograde subduction history to depths greater than 80 kilometers. It was only during exhumation in the subduction channel that we start to see evidence for mixing of different components. But where we do see mixing, I would argue that the discrete mixing events and the sources of those discrete fluids can be identified with chlorine-stable isotopes. And I think we can start to use some of the chlorine isotope data if we increase our spatial scale of the isotopic analyses. We can start to use this to help with model validation for some of these newer generations of fluid models for subduction zones. And so I started out by saying that I think we don't know that much about the details of how fluids move around during subduction. I don't think I've answered that question, but I hope I've shown you that chlorine isotopes can be part of the approach towards getting answers. And there are going to be different answers in different cases, I'm sure. But hopefully the chlorine isotopes can be utilized more to really identify spatial scales of communication. And then lastly, I want to come back to these organochlorine compounds. This was a real surprise. And I think the generation of organohalogen compounds may play a big role in explaining why we have such a wide range of delta 37Cl values in sedimentary rocks, that all sorts of different organic reactions can be occurring in soils and leaf litter, as well as in the marine organisms that I showed you earlier. And if those organochlorine compounds that we've already seen are clearly stable to temperatures greater than 500 degrees, if they're getting subducted, then we have the potential to be dragging down rocks with low delta 37Cl, where it wasn't always obvious how we could do that before. And it's already known from this study by Fudogami et al. That there are organohalide respiring microbes that have been found in the Nankai Trough entering the subduction system there. So if there are organohalide respiring microbes, there have to be organohalides already present. And I think it's not too far-fetched to think that those things are going down the subduction zone. And in that case, chlorine is going to be very fundamentally linked to the carbon cycle during subduction. So not just part of the chloride water cycle. And lastly, chlorine, where it's bound in these organohalogen compounds, has a positive oxidation state. So it's at least +1, which means that any reaction that's turning it from organochlorine into chloride has the potential for every mole of organochlorine that breaks down, we have the potential to oxidize 2 moles of iron. And this may be something worth thinking about in terms of understanding redox relationships in subduction systems and in the mantle wedge. And then lastly, in a shameless ploy to diffuse my critics, I want to come to the parable of the elephant and the visually impaired people who are all inspecting different parts of it. And I would maintain that chlorine isotopes are maybe just down here, the toenails on the toes of this elephant. But elephants do have feet as well as tusks and trunks and tails and so on. So that everything that I've said about the chlorine isotopes has to be part of the overall subduction system. But different systems, different approaches, different chemical systems, different field studies are all going to give us information on different parts of this elephant. So I think there are a lot of different truths out there about what's happening with fluids and recycling in subduction systems, and that we really all need to talk to each other and recognize that we each work on a different part of the elephant. And it doesn't mean that my data are right and your data are wrong. It just means that I'm working on toenails and you might be working on tusks. And with that, I thank you for your attention.
Thank you very much for that fascinating look into how much we can learn from chlorine isotopes. You're in excellent time, so we have time for questions.
But maybe I silenced them all.
I think there's a question here.
So I don't know anything about chlorine, but just out of interest, why do you think that you get preservation of your different signatures during program metamorphism, but you seem to have extensive isotopic interaction, if you like, during exhumation?
Yeah, that's a good question, and I suspect that it has a lot to do with 2 factors. One is simply the dynamics of movement of material in the subduction channel. But I think that's the area where we're slicing and dicing different rock types and juxtaposing them. But also along the exhumation path, the metasedimentary rocks cross a lot of devolatilization reactions. So I think that's where they are most likely to give up chlorine-bearing fluids, and the close proximity of all the different rock types allows for a greater degree of mixing. So. Is that it? Oh, one over there.
Do you see any correlations of your chlorine isotopes with things like iodine-chlorine ratios that might help to support your organohalide complexing that you're considering?
That's a great question, and we're not there yet. This is the point at which I want to take all of these organochlorine-bearing rocks and hand them to somebody else to do a really detailed follow-up study that includes looking at things like iodine and bromine, and also working with the biogeochemistry and the microbes. And this is so far beyond my comfort level. I've gone as far as I can. It's somebody else's ball now, but that's a good question. So.